Hello dear students, welcome to the channel and once again welcome to this new playlist which we have just started. This will be the second video of that playlist. In this playlist we are discussing various mathematical operations which can be performed on signals and systems. So in previous video, what did we see? We saw various mathematical operations which can be performed on a signal. Very fundamental operations, not uh, any complex uh, analysis or complex operations. We just observed how the addition, subtraction, multiplication, integration, and differentiation operations takes place on a signal, like how do you add two signals, how do you subtract a signal from another signal. So we have seen that. If you haven't checked out that video, the link will be flashing on the I button on the top right hand side corner of the screen, so please go and check it out. And today we are going to discuss about the reliability of system. We are going to discuss about the series and parallel connection of the systems, and also we are going to discuss about the cascading of the systems. So without wasting any more time, let's get started with the system reliability, right? So when you want to see a system from a reliability point of view, what do we consider in mind? What do we keep in mind when we want to uh, see a system from reliability point of view, right? So firstly, from a system, the system will consist multiple objects or multiple parts, right? It will have so many elements in it, and combining all those elements we will form a system, right? And by element I mean you can call signals, right? Now from reliability point of view, element is any component or object that is considered in the investigated case as a whole, and is not decomposed into a simpler objects. Like if I want to give an example, you can say an element can be a light bulb, right? It can be a lamp. How so? The lamp, what it will be having? It will be having connecting points of two electrical components. uh, Except for that, you can say uh, a screw can be it can have a screw, like a screw can be a element as well. Oil hose can be an element. A piston in the engine, it can be an element, right? Or if you want to consider a large thing like engine itself, like an engine itself can be a component as well, right? So these individual operations of this individual operation or their groups in a complex manufacturing or building process can be considered as an elements. Okay. So consisting these elements you can form a system, and that system can be classified in two types of systems. First, the simpler systems, and another one is a complex system. So what is a simple system? Simple system, you can say electric light bulb or lamp, right? It has very few components, right? How do you get an electric lamp? You get a light bulb, you have a socket, switch, few wires here and there, plug, and the body of the lamp, and that makes your electric lamp. So it's pretty much basic. It does its components, but there is no complexity in it, right? Now if I want to consider a complex system which has so many different variables playing different parts in the system, so you can consider an aircraft, or even for that matter an engine of an aircraft, right? It contains tens of thousands of mechanical or hydraulic or electrical equipments, right? So many elements it will be consisting. And you can say how if that system is reliable, because each of them can fail, right? So that increases the probability of the whole system's failure, right? The resultant reliability will be depending on the reliability of individual elements and their mutual arrangement, like in the way that you have arranged your elements, and that element itself is reliable or not. So if you arrange those elements in a proper manner, then the suitable arrangement can increase the reliability of the system. But if you don't arrange them in proper manner, then it can also decrease the reliability of your system. So firstly, let's see reliability for a series system. Basically, first let's see what is a series and parallel connection of system. Here in the A picture you can see my signal is going in system 1. It is getting an output, and the output is going in system 2. Then the output of signal system 1 is going in to the system 2, and the output of signal 1 is input to signal 2, right? Same way as the output of signal 2 is input to signal 3, and signal 3 is providing output. So this is your series system. What is a parallel system? In parallel system, what happens, my signal system 1, 2 and 3 will be provided same input or different inputs, but their output will also be different. See, it is pretty much clear that if you have studied the series and parallel connection of resistance or capacitors, then you can also understand the series and parallel connection of systems. It holds no much difference from that. So just to give you a glimpse what is series and parallel, this is how it looks like. Now let's get to series system reliability. Okay, so what happens in series system, when any of its element fails, the system itself will also fail, right? Let, uh, let's say, let's take an example of a motorcycle. So a motorcycle cannot go any further if any of its parts doesn't serve its purpose, like if your engine fails, or your fuel tank loses all the fuel, or your chain doesn't work, or frame, or either of the wheels doesn't work, right? And of course, if even the driver, if there is no driver, your motorcycle will not move, right? So uh, that means all these components need to be function. Either of a component fails, then the whole system fails, and that is what your series system is. So if failure of a component doesn't depend on any other component, the reliability of the system is obtained simply as a multiplication of the reliability of individual elements, right? So what happens here, see, all the components are arranged in series, right? That's why I'm calling it system reliability in series systems. So when when we want to find the system reliability, which means failure of any one component is not depending on any other component, right? So in that case, in order to find the system reliability, what we will do, we will take simple multiplication or simple product of the reliabilities of individual elements. Let's say this r1, r2, r3, r4, r5 up to rn are different elements connected in series. Just the example of bike which we took. So let's say r1 is my engine, r2 is my chain, r3 is a driver, r4 is a rear wheel, r5 is front wheel, and up to rn. So in order to find reliability of my whole system cumulatively, what we will do, we will take the multiplication of reliability of each element, each individual element. Okay, and when we do that, because we are taking reliability, what will happen in practical situations or practical scenarios, the reliability of a series system will always be lower than the reliability of any of its component. Okay, now I will also discuss how, but before going to discuss how, I want to discuss about failure rate or probability of failure. So what is the probability of failure? The probability of failure is a complementary to reliability. So when you find reliability and you subtract that reliability from 1, you will get the probability of failure. Okay, now let's see some examples that what I was saying before, that reliability of series system is always lower than the reliability of its uh, every individual component. So let's say you have a system which has two elements which are connected in series, R1 and R2, and your final value of your final reliability will be R. So we will be taking multiplication of R1 and R2. So the value of R1 is zero point 0.9 and value of R2 is zero point 0.8. Okay, so what will be the value of my R? It will be multiplication of R1 and R2, which means it will be zero point 0.9 into zero point 0.8. So what is the value of zero point 0.9 into zero point 0.8? It will be 0.72. See, 0.72 is less than either of zero point 0.9 and zero point 0.8, which means the reliability has decreased. Your system's reliability has been weakened. And if I want to find the failure rate of the same, uh, for let's say for individual component, I want to find the failure rate. What is the reliability of R1? It is zero point 0.9. So when I subtract zero point 0.9 from 1, what I will get? I will get 0.1, and subtract zero point 0.8 from 1, I will get 0.2. So that will be my failure rates. Similarly, if you want to say see another example, so let's see another example. This time let's consider R1, R2 and R3. R1 is having 0.9, R2 is having 0.8, and R3 is having 0.5. So what will be the final reliability of my system? Because all of them are connected in series, what we will do, we will take multiplication of all of them. So we will multiply 0.9 with 0.8 and 0.5, and multiplying all these factors, we will get 0.36, which is of course less than the reliability of the worst component, which is my R3. What was the reliability of R3? I just told you a few seconds ago. It was 0.5. So what does it means? It means that the reliability of the whole system cumulatively, the series system, is lower than the reliability of all of its components, even the worst of its components, right? Now for till now we have assumed that the reliability of individual part is not depending on its time. Now let's say if the reliability of my system is changing with respect to time, then what will happen, right? If reliability of system will change with time, we can for time component t, we can calculate the reliability of my whole system when the system when every component is connected in series analogy. What will be my uh, final reliability of my system? So we can give it using this formula: R of t is equals to R1 of t into R2 of t into R3 of t into R4 of t into R5 of t into up to into Rn of t. Okay, so pretty much same ways which we have given the formula of reliability when we assume that it is not dependent on time. This time we are considering it is dependent on time. It is changing with respect to time, so we will just take that time instant at which we want to calculate the reliability of my system. Same ways we can calculate the failure rate as well, or probability of failure as well. So in order to do that, again we will calculate the reliability at instant time for my whole system, and then we will again subtract it from 1, and by doing that we will get the failure rate or probability of failure of my system for that time instance. Okay, so that was your system reliability in series systems. Always remember, whenever we discussing reliability in series systems, the failure rate of a series system is always higher, and the mean time between failures is always so shorter. Okay, and again, failure rate of series system is always higher than its individual each of individual components, and the reliability of my system will decrease with respect to time very quickly. Before you know it, it will be doomed. And one more thing, that the more components or more elements you connect in series, the worse the performance of your series will become. Okay, so you can see the very fast drop of reliability in system if you have so many components uh, connected in your series system. And if your system is very important system, then this issue must be addressed for guaranteed operation of your system during certain time operations whenever it is demanded. Because if your system does not function well, and if it is a and if that system is presenting vital role, like let's say operation of aircraft, like if I'm talking about the aircraft engine, if it is having failure rate so high, because it has so many components, right? It must have so many components, and if we connect all of them in series operation, what will happen? The failure rate will be so high, and you cannot drive an aircraft that you would not like to sit in the aircraft that has a high failure rate of its engine, would you? Right? Because it can lead us to catastrophe. So uh, always remember, series operation, what do? We do not consider so many elements, and we never take so many elements in series operation, because the reliability gets too less, and failure rate or chance of the probability of failure increases very quickly. So what is the solution? Let's come towards the solution part, or the parallel system reliability part. So parallel system is, you can say it is not opposite, but sort of complementary of your series analogy. So what happens in what happens in parallel system, that parallel system only fails if all of its parts fails. Let's say for an example of four cylinder engine, right? If you are having a four cylinder engine in your vehicle or in any other equipment, what will happen? The equipment will only fail if all four cylinders will be unable to run, right? If one or two or even all three of them will stop functioning, then still the fourth one will still be able to put the car in the motion, right? even though uh, the uh, even though the power of your car or the speed of your car will be reduced significantly, but your vehicle will still be in motion. It will not be at its best performance, but the performance will be there. It will not be zero. It will be like uh, it will be a performance which can at least take you home, or at least take you a place where you can fix your remaining three cylinder engines, right? So that is your parallel system. So what happens in parallel system? The probability of simultaneous occurrence of mutually independent events equals the product of the individual properties. Okay, so the resultant probability of failure will be this time calculated is the multiplication of uh, probability of failure of each and every component. So see here, we want to find the resultant probability of failure here, and we can represent it by f of t. And if I represent each and every of my elements with f of 1, f of 2, f of 3, and up to f of n, so the resultant um, failure rate or resultant probability of failure will be f1 of t into f2 of t into f3 of t and up to fn of t. Okay, so here again take a note that we are considering failure rate at some instant of time, and for each and every component we are considering failure rate at some instant of time, and for the same instant of time we will be calculating the failure rate or probability of failure of whole system. Okay, whole parallel system. Again, did you notice that in series system what we were doing, we were taking multiplication of reliability in order to find the resultant reliability, and in parallel system what we are doing, we are considering uh, probability of failure, and we are taking multiplication of each and every component to find the resultant probability of failure of my whole system. We were doing the same thing with reliability in series systems, and for parallel system we are doing the same for uh, failure rate or you can call uh, failure rate or probability of failure, right? And same ways as series, see the reliability is complementary of probability of failure. In the series what was there, the failure rate was complementary to probability of failure, sorry, probability of failure is was complementary to reliability of failure. See, f was equals to 1 minus r. Same ways here what will happen, r of t will be equal to 1 minus f of t. So if you want to find the reliability, you will subtract your uh, failure rate or failure rate or probability of failure from 1, and you can find the reliability of your system very easily from that. And uh, we can also take an example here for let's say we are considering a system which has two components, and we are arranging those components in parallel, and again both of them, let's say both of these components have reliability of zero point 0.9. Okay, and if the reliability of each of my component is zero point 0.9, what will be the failure rate? The failure rate will be 1 minus zero point 0.9, which means the failure rate will be 0.1. So resultant probability of failure, what it will be? Resultant probability of failure will be 0.1 into zero point 0.1. So what is the 0.1 into 0.1? 0.01. See, it will be 0.01. So what happened here? The resultant probability, resultant probability of failure is even lesser than both of the elements is failure rate, right? And similarly, if I want to find the resultant probability uh, of whole system, what will be the resultant probability of whole system? R will be 1 minus f of t, which means 1 minus 0.01, which means the resultant reliability will be 0.99, right? So what happened here, the probability of failure has dropped 10 times, and the your reliability has increased tremendously here, right? So if you want to increase your reliability, we can use this parallel system analogy, and this parallel system analogy is used sometimes for increasing reliability by using redundant parts as well. Okay, now please notice what happened here, the distribution is no more exponential, and because of that what is happening, failure rate is not remaining constant anymore. See, failure rate is varying for each and every time interval or each and every time component, and it will be keep changing, okay, from here and there. One more thing, the probability of failure, a failure free operation of system with several parallel parts connected together will be always higher than the best element of the system, which is sort of opposite of what happened in the series, right? Remember what happened in the series? Let's come here and read it one more time. That the probability of failure uh, is complementary to reliability. What okay, I didn't mention it over here, but we discussed that reliability of series system is always here. Yeah, I have written here. See, reliability of series system is always lower than the reliability of any of its component. And what is happening in parallel system? See, the probability of failure free operation of system with several parallel elements all is always higher than that of the best elements in the system, right? So it will provide you the best operation when we connect them in parallel. Okay, so this if you want to increase your reliability, we always use parallel systems. Also, one more thing here, the mean time to failure of a parallel system is always longer than that of its best parts. Okay, and for this reason the parallel arrangement is sometimes used to increase reliability as well, right? Now what is the best operation? Best operation is to find the balance between series and parallel connections. So in order to do that, we form combined arrangements. As you can see here in this figure down here, we have arranged a combined arrangement. So in some system we have to do it, we have to take series and parallel arrangements together, and we can find the resultant reliability with using step-by-step solution and gradual simplifications, the way we solved in the series first and then again for parallel, right? So what can we do? The group of elements which are arranged in series will be replaced by one element with equivalent reliability parameters, right? And what will we do with parallel elements? So the parallel elements can sometimes be also replaced by equivalent element, and the situation is easier if the time dependency of reliability does not need to be considered, right? If you want to consider the time dependency, then it gets complicated, right? Because for each time instant you have to calculate it, then again you have to calculate it, you have to do all the math, right? So if reliability is characterized by failure rate, then the failure rate of parallel arrangement is not constant, and we cannot do simple accurate analysis of system, right? So that solution, simple solution does not exist, it becomes complex. But if you want to do simple, you can only find approximate values, but best results can be obtained using numerical simulations methods. So if you want to find results rather than calculating mathematically, go for numerical simulations. Uh, you can find better operations there. So that was your series and parallel systems. Now quickly coming to the cascaded series parallel systems, or cascading of first we will discuss the cascaded series interconnection. So let's consider this series, a series of series or cascaded interconnection of uh, this this system which you are seeing in the image. It is having input x, input signal is x, output signal is y. Two systems are here, h1 and h2, and uh, signal x is going into the system h1 as an input, and h1 is producing z as an output, and that z is fed to system h2 as an input, and h2 is giving y as output, right? So if you want to represent this system mathematically, you can represent that what is z for h1, z is output for h1, right? So z will be h1 into x, right? Same is what is y for h2, y is output for h2, And what is the input for h2? H2's input is z, so you can represent it this way: y is equals to h2 into x. Now if you want to represent the whole system cumulatively, whole system combined, you can represent it this way. You can represent y is equals to h1 in dot h2 dot x. Sorry, it will be h2 here. I think there is some mistake. It should be h2 here. Okay, so you must have a question that does the order of this two systems h1 and h2, does it matter or does it not, right? Because we are doing multiplication here, but in reality the order matters. Okay, how it matters? So first cascaded system is not necessarily equal to the second cascaded system, which has shown in the figure here. See, in the first figure, it is we are following the same analogy as this connection, but what did we do in the second one? We replaced h1 and h2, we toggled their positions. So what happens that the output for the first system, which is shown here, will be y is equals to h2 dot h1 dot x, and here it will be, I mean in this one the output will be h2 dot h1 dot x, and for this system it will be h1 dot h2 dot x, right? But normally h1 dot h2 is not necessarily be equal to h2 dot h1, because what happens, see, if h1 is having some different values, some different parameters than h2, then the output z for this system will not be equal to output z of this system. And if output z of this system will not be equal to the previous system, then how will our final output y will be equal to this system, right? So it is not same, but there are some special cases for which it also can be equal, but for most of the cases, for most of the times, it is not necessarily be to equal. Now let's consider the case of parallel interconnections. So again here we are taking input x and we are feeding this input to both of my systems h1 and h2 simultaneously, and the output from both of the systems are added together. And when we add outputs of both of the system, by the way, output of h1 is y1, as you can see here, output of the h2 is y2, and the final output, the addition of y1 plus y2, is y. Okay, so if in order to represent it mathematically, you can see y1 is equals to h1 dot x, which makes pretty much sense. Y1 is the output of h1, so h1 into x is the signal which fed in, which was the input to system h1, so y1 is equals to h1 dot x, and same way as y2 is equals to h2 dot x. See, y2 is the output, h2 is the systems, and h1 is the input signal, right? Now then what we are doing, we are taking sum of both these outputs y1 and y2, and we are finding the resultant output will be y. So y is equals to y1 plus y2. So in this case what will happen, y will be equal to h1 plus h2 dot x, right? But h1 and h2 will be in bracket, right? h1 and h2 will be in bracket because what did we do, we took x common because the input of both the systems were same, right? So we took it out. So you can represent parallel interconnections using that. And I think we have stretched this lecture a little bit longer than the usual lectures, but no worries, I think this will be clear to you. So if you have any doubts or any queries related to this lecture or any other lecture or anything else, please feel free to mention it in the comment section below. If you want to if you want to give any feedback or if you have any suggestions for me, feel free to mention it in the comment section below. I will try to solve your doubts and reply your comments as soon as I can, and I will be trying to connecting with you all. So I'm ending this lecture here. I will be seeing you next time. Thank you very much for listening, and Goodbye.